This is the review of chapter 6. The first question is asking to classify each of the following reactions as an addition, elimination, substitution, or rearrangement. So if you look at the first reaction, we are substituting the Br with an OH. So it is a substitution reaction. In general, in substitution reaction, one or more of the atoms are substituted by a different atom. So this is an example of substitution. In the second one, here if you look, we are adding, the second one is a elimination reaction. And the third one, where's this one? Yeah, this one, second one is an elimination, where you have eliminated a small molecule like HBr, and then the third one is an addition reaction, where you have added the hydrogen to the double bond. Okay, so for example, if I draw this out, it looks like this. There are two hydrogens on the carbon atom, but now you have added another hydrogen molecule, right? So you get rid of the double bond, and now you have all hydrogens on the carbon atom. So it is an addition reaction. Generally, addition reactions are shown by alkenes, alkynes, etc. Now the next one here, if you'll see that the matching or filling up the blanks here. So it's asking, the first question is a species that lies at an energy minimum between steps in a reaction. It's reaction intermediate, right? So for example, it's saying that, say, if you are plotting the energy versus reaction progress, then if you draw the graph for it, so that lies in the energy minimum between steps. So if this is a two-step reaction, this is the energy minimum, right? So that is the reaction intermediate, because this is my reactant, this is my product, and here is my intermediate. Alright, the next one is asking the energy needed by reactants to reach the transition state. So from going from the reactant here to the transition state, how much energy is required? That is an activation energy, or C is the correct answer for that. Okay. And then the next one is asking a reaction where delta G is negative. So in this case, like the way I have drawn, where the reactant is at a higher energy state than the product, so the difference in energy here, if you see, delta G is negative, so that is an exergonic reaction. Okay, when the products are at a lower energy state than the reactants, that is an exergonic reaction. So the answer is E there. The next one is the formula for calculating delta G, which is given as RT natural log K, negative R of RT. Temperature R is a constant, and it is natural log of equilibrium constant. That will give you the value of the change in free energy. Number 5, the highest energy structure in a reaction that's shown here. So that's called as the transition state. This one, see, the highest energy structure, that's a transition state. And okay, so that finishes that question. Let's do number 3 now. Explain homolytic and heterolytic bond breaking using examples. So the first example is taken as a chlorine molecule split. Generally, this happens in the presence of light, and it can split into two radicals. That will be a homolytic bond breaking. Homolytic means when both the elements each take one electron. Both elements that form a bond, right? Each of them take one electron. So this generally happens when both the elements are of equal electronegativity. Okay? So homolytic bond breaking happens in this case. That's an example of a radical reaction. Heterolytic bond breaking is where one of the atom, like in this case bromine, is more electronegative than carbon, and it pulls the electron towards itself, creating a positively charged center on the carbon. So this is a polar reaction, and that's an example of a heterolytic bond breaking. In homolytic bond breaking, you use this fish hook arrow, right? This is a fish hook arrow where half the arrow is drawn, and in heterolytic bond breaking, you actually use the full arrow like this. All right. It's asking what's the difference between a radical and a polar reaction, explained using examples. So that just now what we talked about, that is the difference between a radical reaction and a polar reaction. In radical reaction, it ends up in the formation of unpaired electron species, which are called as free radicals. And polar reaction, the intermediates have charges on them, like for example, you form carbocations, and then the final reaction where there's nucleophile, electrophile reactions to form the product. Now the next one is asking you about adding curved arrows to the following polar reaction. So in this case, we have to look at the products, and you see that in the product there is a double bond between carbon and oxygen. So the way we can do it is take this pair of electrons and make a double bond here, but at the same time, see, chlorine has been removed here, right? So you have to remove the chlorine, taking the pair of electrons with it, so that gives us the chloride radical. Next question is asking you to draw an energy diagram for a two-step reaction in which both steps are exergonic. So that means in both cases your reaction should be in the higher energy side and the product should be in the lower energy side. So here in the first step we have an intermediate formed which is at a lower energy than the reactant, and again the next step, see, we have a product that's at lower energy than the intermediate. So that fulfills the condition of the question. Then it's asking you to label all parts. Reactant, this here is your reactant. Then it's asking your product, it's your product. Then intermediate is somewhere in here in between. And then overall delta G double dagger, this means activation energy. So and this is the activation energy 1 and this is activation energy 2. So you have to show both of them. The first one looks like smaller than the second one, so the first step is a faster step than the second. Okay, so whichever has greater activation of energy, that will be the slower step. So it looks like the second step is slower than the first, and so the second step should be your rate determining step also. And then delta G, in this case here we have reactants. Actually the drawn. The delta G should be drawn from here to here, right? So that's your delta G, change in free energy between the reactant and the product. Okay, so it's a negative, so it's an exergonic reaction. Okay, then it's asking write down here the complete mechanism for a free radical reaction using any example. Label the initiation, propagation, and termination steps. So we can take the example here, say for maybe this one, where you have an alkane reacting in presence of light and halogen, say bromine, to give this product. Okay, so if we take this example, then you can do the different steps for it. Say for initiation, you will have the first step would be where bromine reacts in presence of light to give Br radical. Okay, so 2Br radical, that will be the first step, that's initiation. So basically you can also show it like this, Br atoms, right? So you can, with arrows, you can show that these both take 1 electron each. Remember, this is a free radical reaction, so both of them take 1 electron each to give you 2 Br radicals. Okay, you can, if you want, you can show the other electrons also. But sometimes we just show the unpaired electron separately. Okay, Alright, so that's your initiation. In propagation, then, which is your next step, in propagation you should always end up with a free radical in your product side. So the Br radical that was formed in the first step is now going to react with your alkane, and here I'm going to show the hydrogen, because the hydrogen is the atom that is getting replaced by Br, right? So I'll put the hydrogen there, and then the way we will draw the arrows is from the bond to a homolytic bond formation, and then the other electron actually goes and stays at the carbon atom here. So what we get is HBr as one product, and then the other radical that's formed is this one. Okay. So since in a propagation you always end up in formation of a radical in the product side, so this could be a propagation step. Okay. And then finally in the termination, you can add more propagation steps if you want to, but just showing one as an example. In termination, two free radicals combine. So in this case, I'm showing an example where this radical combines with another Br radical, right? So see, the way you will show bond formation is again through half arrows, and then you end up in the formation of a product, which is the one that's shown over at the top. So 3 steps. Only in free radicals you have 3 steps, not in polar reactions. So that's the example. Next is asking, write a complete mechanism for a polar reaction using example from the text. So here we have a alkene reacting with HBr. So the first step would be nucleophilic attack. So this is my nucleophile. Here is my electrophile. Okay, so the hydrogen is electrophile. A reaction happens in this manner, where Br pulls off the electron, hydrogen is short of electrons, so the new pi bonds, which are the double bonds, they're rich in electrons, they are my nucleophile. They attack the electrophile and you get a carbocation. Intermediate is a carbocation. This is a carbocation. It's called carbocation because the positive charge is on the carbon atom. Then Br goes and attacks here. Now this becomes my nucleophile, this is my electrophile, and you get the final product. So that's exactly what's asking in here about the top reaction, that which is a nucleophile. Your pi bond is your nucleophile, your proton is electrophile, and the carbocation is the intermediate. And then also show curved arrows, which we already did. And then finally we come to the IR topic here. It's asking us to match the spectrum with the given compounds. So if you look, we have a carboxylic acid. Okay? So carboxylic acids are pretty easy to identify in an IR spectrum because you have that very broad peak in the range at the 3,500 centimeter inverse. Similarly, ketones of 1600 to 1750 or so. So that's again easy to locate. This is a ketone. Then alcohols, again, they have more like a smooth tongue kind of structure, again close to the 3000 centimeter inverse area. Cyanides appear as a sharp peak in the range of 2000 to 2400 centimeter inverse, right? So cyanides are also identifiable. Same thing, amines, okay? And that if it's a primary amine, you will see two, like a fang kind of structure, is due to the NH stretch. And then finally, a aldehyde, which will have a carbonyl, plus it will have the stretches for the carbon and the hydrogen, okay? So keeping that in mind, let's go and check the spectrum. If you look at the first spectrum, you have there is absence of any peak near the carbonyl area, so it cannot be a carbonyl. And then it has got this two fang kind of structure, so that corresponds to the amine. Okay, so that's my amine here. And then the next one is the sharp peak near 1700, which is characteristic of a carbonyl, so that has to be a ketone, but the carbonyl, but then it's also showing this carbon hydrogen stretches, so it has to be the aldehyde. Then the next one is the OH, like I was saying, the smooth tongue kind of structure, which is again clearly identifiable. That's the OH stretch. This over here is again the CH stretches. And then the fingerprint region, we don't have to worry about it. And then finally, let's see, well, we have two more of this. And again, here we have, see, the ketone. Now the ketone is identifiable easily from an aldehyde because, see, it doesn't have that carbon-hydrogen stretch, right? This is just a carbon-hydrogen stretch of the other rest of the molecule, but in a aldehyde, if you recall, the carbonyls carbon is connected to a hydrogen that appears separately in an aldehyde. So this cannot be an aldehyde. This is a ketone because those stretches are absent. Okay. Then the last one is again the carboxylic acid. This is the very broad. Okay, so this is your OH peak from the carboxylic acid, and then as well as it also has a carbonyl. So you can match all the compounds with the different spectrum. And then finally we have the cyanide, which has this sharp peak here in the region between 2000 to 2500. It's characteristic of a cyanide, so that becomes your cyanide structure. Okay, so this concludes the revision of chapter 6, and chapter 7 has been posted separately in a different video.